Hello everyone, this is the solution video to quiz 4. Now here the question was to basically calculate the Ackermann data that is necessary to use the Ackermann formula like this, where product, coefs, I, length and for loops were only available and everything else was basically not available. Yeah, and we use A and B matrices, and then we have some poles, and we want to basically come up with phi and PDA, so that phi is inverse times PDA, and this gives us basically the controller. We had also a test script here that was more of checking if the poles are actually assigned like they should be, but of course it's important to check if PDA and phi is correct. So let's actually dive into it. This is basically the test script that we have here, and this is basically the function that we need to code here. So let's begin. We need first of all a symbolic S, and then what we can do is we can just use basically PDS equals the product of S minus poles. Now, you don't actually need to do anything else because poles has all the poles in it, like 1, 2, 3, 4. And this is basically carried out element-wise. So, and then the product of that is the definition of a polynomial, actually. So S equals poles. So these are -1, -2, -3, and -4. So this should be S plus 1, S plus 2, etc. So let me actually define phi equals 0, PDA equals 0, and then let me write down what PDS is. And what I can do is test it, and you can see S plus 1, S plus 2, S plus 3, and S plus 4 are the roots of the polynomial. Then we have phi and PDA, and since these are 0, we get singularity, and K is none, and everything is none, but that's not an issue. So this is the polynomial. And what we need to do is we need to substitute A into it. So I need the coefficients of that, but I'm not going to use the substitute method that is available in the symbolic toolbox. And the reason behind that is going to be the following. Whilst I'm here, let me just convert it into a double. There we go. So now, let me actually check this out. There we go. Now these are the coefficients. And if I plug in S equals A, this is a power of A, this is another power of A, this one too, and this one too. But this one here is basically a scalar term. And if you use subs from the symbolic toolbox, this would be a fatal error, because in MATLAB you can add a scalar to a matrix, but that's not really what we're after here. Mathematically, this is not possible, and what we want to do is we want to multiply 24 with the identity matrix so that it can be added to matrices. So during the construction of PDA, this is quite important, and if you don't do that, and if you are using MATLAB, you will get a erroneous output, because 24 can be added to matrices in MATLAB, but that shouldn't be the case because we want to add it 24 times the identity. So therefore what we have to do is we have to get around to do that. So what I'm going to do is I'm going to use coef and times the identity n. So it seems like I need the order of the system. So that would be the length of coef minus 1. So since n plus 1 coefficients will be there, so n will be the order of the system, and identity and PDA is going to be calculated like this. Now, of course, you could maybe come up with some crazy strategies like subtracting coef n times identity, or just getting rid of that part and try to use subs again. That could be the case, but I'd like to use just a for loop from 1 up to n. I'm just going to do it like the following. I'm going to add to PDA coefficients I, so the first coefficient, for example, times a to the power of something. So if I use I, it would be coef 1 times a, which is not correct, because this is the highest order term. So I should place in n minus I. But in that case, if n is, for example, equal to 4, then I is 1, then we would have the third order, where since n is 4, it should start with 4, so I should add 1 to it. So that I start with n and go down to 1. And this should basically give me PDA. So you can see I'm just multiplying everything with the corresponding matrix power, but I use the identity times the last element so that I don't cause some issues here. So there we go. This is basically PDA. And then we need phi C, or phi actually, and we start with B here. And I'm going to use this for loop here. And now phi is going to be extended phi without the coefficient, without that, times B. There we go. Now, of course, this is not the order here, so it should be basically I. So it should be I. And yeah, we should start with 1. So B, AB, A square B, up to n minus 1 instead of n. So that would then give us phi 2. And yeah, that's actually it now, because as you can see, once I run the script, I get -1 up to -4. These were the initial pools that I wanted to assign that to. And I get also the vector that looks like it should be correct here. So if we check it out, we can see, yeah, -4, -3, -2, -1, and then 16, 32, 23, 9.5. So even though this doesn't check really if PDA and phi is correct, essentially it should be working like this. So it seems like it should be correct, otherwise it wouldn't work. So you can use then these to calculate basically the Ackermann data, and then yeah, you're good to go. You can also use this with A transpose, C transpose, and poles in order to basically obtain the observer version of this. But then again, you need to be careful about the transposes. So yeah, this is basically the solution.